So hello to all comp222 students. Hope everybody's staying safe, staying healthy, staying at home as much as possible. And today I'm going to go over chapter 5, the key sections that we're going to need for midterm number 3. So chapter 5, the title is Memory Hierarchy, so it deals with various levels of memory. We're going to go over caches. We're going to go over virtual memory and also talk about how main memory sits between the two. So as an introduction, just to show what this is all about. So with memory, two key things we're concerned about. One is called temporal locality. This is the idea that when you reference something from memory, chances are you're going to be referencing it again soon. So usually we reference the same data locations multiple times. Spatial locality is the idea that if you reference one data location, odds are you're going to also reference its neighbors, the nearby addresses, soon. So this sets the stage of how we would need to organize memory. So we have what's called a memory hierarchy. We have different levels of memory. We have our processor, and we have different levels. And the idea is the closer you get to the processor, the size of memory will be smaller. The closer you get to memory, smaller, it's going to be referenced more often. And at the same time, because it's smaller, it's also going to be faster. So the smaller the memory, the faster it is. The further away you get from the processor, memory gets larger, but at the same time it's going to get slower until you get all the way down off of RAM, static RAM or dynamic RAM, and when you get to the magnetic disk, the hard disk, then it's going to be the largest memory we're going to have, but it's also going to be the slowest. Since the closer you get to the processor, we said it's smaller, we're not going to find everything we're looking for. This is going to be a subset of what's in this level of memory, which is going to be a subset of what we have in this level of memory. So we're going to put things that we use more often in the smaller set of memory, things used not as often in here, and things not really used that often in here. But since this is a subset of this and this is a subset of this, everything we have here is going to be here. Everything we have here is going to be here. But the opposite's not true. Since this is bigger, not everything we have here is going to be here. Not everything we have here is going to be here. So sometimes we'll find something in this first level of memory. Sometimes we won't. If we find something, I'll show this. If we find something, we come directly to this level of memory. I guess it's going to be this little blue block. So we'll grab it and return it to the processor because that's what we're referencing. That's what we want to access. There will be a copy of this blue block in the next level of memory. Chances are this is the cache and this is our main memory. So the cache is just a subset of the main memory. And we're going to have a copy of this sitting here in main memory, but not everything in the main memory will find a place in the cache because the cache is just a small version of main memory. The odds that we find what we're looking for in the cache, that's what we call the hit rate, the probability that we find what we're looking for in the current memory hierarchy, which is the cache. So the probability that we find it is the hit rate. Usually it's about 80 to 90%. The opposite, the miss rate, is a probability that we don't find what we're looking for in our current memory hierarchy or in our cache. So we find something, the odds are that's part of the hit rate, and if we don't find what we're looking for, that's part of the miss rate. If the hit rate's about 80 to 90%, the miss rate is just 10 to 20%. Now the time it takes to actually access the cache we call the hit time. So the time it takes to go to the cache, find what we're looking for, and return it. If I go back to my picture, that's the time it takes for the processor to request something from my cache and then return it back to the processor. That's called the access time. That's what's also called the hit time. If I don't find what I'm looking for, that's what's called the miss penalty. So this is the time it takes to grab something from the level where the reference is actually at, and then transmit it to the next one, so then it can be passed back to the processor. So really that's this time right here. So if I went through the cache and I didn't find what I was looking for, I got to go down to the next level, the main memory, find what I'm looking for, and because I don't want that to happen twice, I don't want to reference the cache again and say, well, it's a miss one more time. I want to copy from the main memory into the cache. So the time it takes to go from the cache to the main memory, to find what I'm looking for, bring it to the cache, so that the cache can deliver it to the processor. This double-sided arrow right here is my miss penalty. So this double-sided arrow is my hit time. This double-sided arrow is my miss penalty. So that just gives an overview of chapter 5, what we have to deal with a cache. So now let's look at the cache in more detail. We're going to skip section 5.2. This just gets into some hardware descriptions of memory. I guess one good thing to pull out of this is a picture. Here's our processor, here's our cache, here's our main memory. And then we could also have one more level, the magnetic disk. We're not going to get into this, mainly because a lot of times we don't even use magnetic disks anymore. We use solid state drives. Even though magnetic disks still exist, it's a little bit archaic technology. So we're going to bypass this section. We're not going to get into the actual physical heads and reading of the disk. We're going to bypass this. We're going to bypass tracks, sectors, seek time. If you want, you can get into this. This will not be material for the midterm. So going on to caches, we saw a brief overview. So what is a cache? As we said, it's a subset of main memory. This picture shows it best. So this could be our main memory right here. We have various blocks in our main memory. And we're going to have a subset of these blocks sitting inside my cache. This is a very small cache. Usually it's bigger than this, but just to show by example, this is a cache that has 8 entries, so 8 blocks. We're going to number them 0, 1, 2, 3, 4, 5, 6, 7 in binary representation. In memory, we're going to have a lot more blocks. We're going to go from 0 on the left here all the way up to, I'm going to do some quick binary conversion. This would be 7, 14, 29, 30, 31. So we're going to have 31 blocks of our main memory, and we're going to have 8 blocks of our cache. And each of these blocks in main memory is going to find a place to fit in the cache if what we're dealing with is what's called direct map. Direct map means there's exactly one place where each of these blocks in the main memory can fit in the cache. The way we do this, you can think of it, if you learned in comp222, as a hash function. Really, we're taking the address, and we're doing modulo. We're dividing by how many blocks we have in the cache. Since we have 8 blocks, we're going to divide by 8 and take the remainder. Easy way to think about it is in the main memory, block 0, 1, 2, 3, 4, 5, 6, 7 would find their place in the cache at block 0, 1, 2, 3, 4, 5, 6, 7. That's why block 1 of main memory would fit into block 1 of the cache. Block 5 of main memory would fit into block 5 of the cache. Once you go past 0, 1, 2, 3, 4, 5, 6, 7, we reset. So block 8, if you do 8 divide by 8 and take the remainder, goes back to 0. So block 5, 6, 7, 8 will go back to block 0. And then 9, as it's shown, would map to block 1, because 9 divided by 8 is 1, remainder 1. Since the remainder is 1, it would fit here. Same thing. Block 13. 13 divided by 8 is 1, remainder 5. So the remainder is 5, so it would fit into block 5. And the same goes for everything else. One thing about this picture, it looks like block 1, block 9, block 17, block, do some quick conversion here, 3, 6, 12, 25. I guess that's 25. Block 25. So 25, 17, 9, and 1 could all coexist in block 1 of the cache. That's not true. Only one of these, that's shaded in gray, is going to exist in the cache at one time because they all fight for the same area. Only one of them can be there. Same thing goes with the light blue here. Block 5, 13, 21, 29 would all fight for block 5 of the cache, but only one of them can be there at any given time. This is why we're going to have misses, because if block 1 is sitting in, of main memory is sitting in block 1 of the cache, and we try to search for block 9 in the cache, block 9 is not going to be there because block 1 already is. So searching for block 9 in the cache would give us a miss because somebody's in my spot, block 1. So we're going to get misses in this case when you're looking for one block but another block is in your spot. So another way to show this, if maybe I can make this a little bit bigger, more readable. So we're going to have a valid bit that says whether or not we actually have an entry in my cache. If we don't, we're going to mark it with just N for not valid, and all the ones that are valid are here. So for example, if I try to find block, what is this going to be? It's going to be 16 plus 7, so this is 23. I'm looking for block 23 in my cache. If my cache has 8 blocks, it's going to be index 0, 1, 2, 3, 4, 5, 6, 7. And so I'm going to take, in binary, the easy way to do it, I'm going to take the last 3 bits, since there's 8 blocks. I can take the last 3, if I can just highlight the last 3, not the whole thing. So this means block 7 is going to be my index. But how do I know if this is in the cache or not? It says the entry is valid, but how do I know that it's actually in there? I got to look at the first 2 bits as my reference. So this is what's called a tag. Let's see if there's a definition up here earlier. There it is. So this is a field that's used to actually reference the memory location. So 1, 0 matches what's inside my cache here of 1, 0. So the tag matches. That tells me that, in fact, this reference is located at index 7 in my cache. So I know that the data is, in fact, address 23. What is this data? We don't know exactly. We just say it's whatever's in memory location 23 has a copy in my cache at index 7 or row 7 of my cache with a tag or an ID of 10. So this is going to be there. This one's not. How do we know? Because we have 0, 0, 0, which means row 0. and I guess we had to fetch this from memory. We will fetch it from memory, but initially, if we look at row 0, we did not have tag 10. This shows that we added it later on. There's actually an animation, so we added it later on. So now, after the fact, we will have a tag of 10 for row 000. So this will be there afterwards. And the last one we'll show is here. If we have 101, that's going to be my index. We take the last 3 bits. Once again, since there's 8 blocks in the cache, take the last 3 bits of the address, 101. That's my index. I look for it, and I find out it's not valid. So none of the tags are going to match anyway. So 11 will not find a match because we don't even have a tag, because the entry is not even valid. So we can go through various memory references, and you can go through this in the book and see how everything fits, everything matches, everything goes through. Little participation activities if you want to step through. What I'm going to do is show an example here from the exercises. So if we go into the exercises, I'm going to have to go back here and chapter 5 onto the exercises in section 5.19. So a good example of this is exercise 5.2, where we're going to look up various memory references in hexadecimal and see how they fit into my cache. Now they give us some information here, namely we have 64-bit memory address references. Doesn't even have to be this big. The key thing about this is we want to find out, if I have these hexadecimal references, what is the binary word address, what is the tag, what is the index, if I'm dealing with 16 one-word blocks. So 16 one-word blocks means each block contains a single word. We're going to be referencing words. And since I have 16 blocks, in the previous example we had 8 blocks in the cache. This time I have 16. Since I have 16, I'm going to be pulling off the last rightmost 4 bits to tell me which block I'm referencing. So now we're going to move on to the exercises. So we'll start with 5.2. So as we showed, we had 16 one-word blocks. So I'm going to need, since I have 16 blocks, log base 2 of 16. Sorry, this 2 should have been at the bottom. It's not log squared, it's log base 2. So I'm going to need 4 bits, since I have 16 blocks, 4 bits to identify which block, which one of the 16. So I need 4 bits for this. Since we start off with 64 bits for the address, we take off the 4 bits. We have 60 bits remaining for the tag identifier. So as we showed in the exercise, the word address we start off with in hexadecimal 03, then B4, then 2B, 02, BF, etc. We convert this hexadecimal into binary as such. So 03 would be in binary 0, 3. B4 would be, there's B, 11 in binary, B, 4. 2B would be 2B, since B is 11. And the ease of doing this is, since the last 4 bits is going to be my block. I can just read this 0, 3. 3 will be my block index, and the 0 will be my tag. So 0, 3, B4, 2B, 0, 2, BF, etc. Key thing about this is whether there's going to be a hit or a miss in the cache. This might not be the best example because, as you notice, every single one of these is going to be a miss. Why a miss? Well, the only way to get a hit is if you reference the same index twice with the same tag. But notice all of these are unique. We never hit the same index with the same tag twice. The only time when we actually hit the same index is here. We hit index E, which is 14 in binary. So that'd be block 14 or index 14, or you can think of it as row 14 in the cache. This is the only one we repeat. But when we repeat it, we have a different tag. So there's a mismatch. So this is not the best example probably because every single time we're going to get a miss in the cache. We never hit the same thing twice. If we expand this in the next part of the question, 5.2.2, instead of 16 one-word blocks, we're going to have 8 two-word blocks. This time I got the subscript right. So log base 2 of 2, why 2? Because we got two-word blocks. So I need to say which of the two words within the block I'm looking at. So I have 1 bit for the offset to tell me, is it word 0 or is it word 1? That's what offset means, within one of these 8 blocks. So we break each of the 8 blocks into possibility of 2 words within the block. So we break it down further than a block into words. Since we got 8 blocks, I'm going to need log base 2 of 8 to tell me now which block identifier. Once again, we've set aside 4 bits out of the initial 64, so we got 60 left for the tag. Once again, most of these bits in the front are going to be 0, so I'm just looking at the last, how should we say, I'm looking at the last 4 for the block identifier, 3 bits for that, 1 for the offset. So that's going to be the last 4, and everything before the last 4 is going to be my tag. But since most of this is 0, I'm just looking at the last 4 of the tag. So we have the same addresses here: 03, B4, 2B, 02, BF, 58, BE, 0E, same as before. What changes in this case, excuse me, clear my throat, is the tag is going to be the same, but this time, instead of just 4 bits for the index, I'm going to have 3 and set aside 1 bit for the offset. So we have 1 bit, the last bit here is 1, so that's my offset of 1. Last bit is 0, so the offset's going to be 0. So this means word 1 of index 1. This means word 0 of index 2. That's why I have 0 here, then I have 2. It's going to be these 3 bits to represent 2, index 2. These 3 bits, 1, 0, 1 to reference index 5 with an offset of 1, and so forth. The difference here is we're actually going to get more hits. We get a hit here, we get a hit here, and we get a hit here. Why? In this case, I'm referencing index 1 for the second time. This is the first time I did it. Here's the second time, and I have the same matching tag. So the second time I reference this, it will be in fact a hit. Same thing here. This will be a hit because for the second time I'm referencing index 7. Here's the first time, here's the second time, with a matching tag of B, And here I have a hit because this is the second time I reference index 2. This is the first time up here. So I reference index 2 with the same tag of B. So we get a hit. So this time I get 3 hits out of 12. So it's better than this one where I didn't get a single hit. Excuse me, clear my throat again. And then we can extend the problem to compare 3 different caches. Once again, we have a 64-bit address, so we're setting aside the first 60 bits for the tag. And as I said, we're just going to write it as 2 hexadecimal digits since the leading digits are all 0. So that represents this. There's my tag. There's my tag. There's my tag. And how these caches differ, the first one, we're just having an entire 3-bit index. The next one, we have a 2-bit index and 1-bit offset. And the third one, we have a 1-bit index and a 2-bit offset. So we can think of this as 3 bits, so 8 blocks. In this case, 2 bits, so 2 squared is 4, so 4 blocks. And 1-bit offset, so we have 2 words per block. In this case, 1-bit index, so 2 to the 1 is 2, so we'll have 2 blocks. And a 4-bit offset, so we're going to have 4 words per block. Sorry, my throat's kind of rough here. Try not to cough as much as possible. So we take our address once again, and now we break it up. One thing I should have noted, since we're only dealing with the last 3 bits in each case, even though we wrote it this way as binary, really we got to take these 4 bits and the next one. I wish I could just highlight this. It's going to try to grab everything if I do that, like that. But these 4 bits and the next one really represents the tag. So it'd be 0, 0, 0, 0, 0, which is going to be 0. Write it in hex because really we're taking this bit, which I wish I could highlight by itself. This 0, 0, 0, 0, that represents this 0, the last one. And the first 0 here represents this. That's why over here we have 1, 6, because I take this 0, 1, 1, 0. So 0, 1, 1, 0 is 6. This 1 by itself is 1. Over here we got 0, 1, 0, 1, which is 5. And the leading bit here is 0, and so forth. And we're only dealing with the last 3 bits to tell us the index and possibly the offset. Cache number 1 we said is just a 3-bit index, so we just take the last 3 bits. 0, 1, 1, that's 3. 1, 0, 0 is 4. 0, 1, 0 is 3. 0, 1, 0 is 2, all the way through. Cache 2, the difference is we take 2 bits for the index, 1 bit for the offset. So the last bit, actually we're not even dealing with the offset, we're only dealing with the index. So 2-bit index, I'm going to pull off this bit and this bit, the 0, 1, that's 1. Here we got 1, 0 is 2, 0, 1 is 1, 0, 1 is 1, 1, 1 is 3, all the way through. So this bit and this bit, once again I wish I could just highlight both of these, but it's going to try to grab the entire 4-bit section. So the second and third bit of this group of 4 will be my index. And for cache 3 we just have a 1-bit index, so it's just going to be this second bit of the group of 4. So 0, 1, 0, 0, 1, 0, 1, 1 as we go through, because the last 2 bits would be set aside for the offset. So here's all the cases. How they differ is how many misses and how many hits we have. In cache 1, the bad news is everything's going to be a miss. because we never hit the same index twice with the same tag. Here we have index 3, and even though we're referencing index 3 again, notice different tag. So that's going to be a miss. Here we have 4 with a tag of 16, but the only other time we have 4 is down here, but our tag is different, it's 05. Here we have 2 as an index, but the tag is 0, versus over here, the tag is 17. And also here we had 5, even though we had 5 before, we have different tag. So we're never going to hit the same index twice with the same tag, so we're never going to have a hit. In cache 2, it turns out better because here we have a hit because we're referencing index 3. And why this actually is a hit is because up here we have index 3 and we had a tag of 17, just like we had right here. So we hit the same index twice, so we get a hit. The other hit we're going to have is right here because we're referencing index 2 for the second time with the same tag. So we get a hit. Those are the only 2 hits we get. If we go the route where we only have 1 bit for the index over here, actually makes matters worse. The only time we're going to have a hit is right here because we're referencing index 1 with a tag of 17, which we previously did right here. All the other ones are misses because even though we may think we'd have another hit here somewhere, for example here, because I'm going after index 1 with a tag of 16 the second time, because here I have index 1 with a tag of 16, but this gets overwritten because we only have 2 indices. So in between this and this, a lot has happened. We've been changing the tag repeatedly for index 1. So we overwrote this one. That's why this tag no longer applies to this index by the time we get down here. That's why we're going to end up with a miss. So in the first case, we had all misses. Second one, we had 10 out of 12 misses. Third one, we had 11 out of 12 misses. That's the next part of the question down here, where we compare them. And cache, I got to correct my spelling here. It's not cache C, it's cache. Sorry. Check my spelling. So this cache, the miss rate is 12 out of 12 times. So 100% of the time we're going to miss. How this is going to affect my total number of cycles, we measure this by how many accesses we did times the time to access plus how many misses times, need a left parentheses here, the penalty time or the time for handling a miss. We call it the miss stall time. If we go back to the question, over here we can see our parameters. And we said C1, cache 1, as we said, has 1-word blocks, so 16 bits. And here's all the penalties. C2 had 2-word blocks and C3 had 4-word blocks, as we showed. And then we want to compare the miss rate or see which designs the best. And in all 3 cases, the miss stall time is 25 cycles. Cache 1 has a access time of 2 cycles, cache 2 3 cycles, cache 2 3 cycles, cache 3 5 cycles. Using all these parameters, and we compare. There goes the plane overhead. You can hear it. Not sure if you can hear it through the microphone. It's pretty loud here. So we have 12 out of 12 times, so 100% miss rate. And we had 12 accesses here. And as we said, the access time will be 2 cycles plus how many misses? Well, all 12 were misses with a miss stall time of 25. We do the math, we end up with 324 cycles. Cache 2, we missed 10 out of 12 times. So it's an 83% miss rate. How that changes our answer? Well, we still have 12 accesses. This time the access time in cache 2 is 3 cycles, so we change that. We had 10 misses, not 12, 10 misses. Those 10 misses are going to cost us 25 cycles. So a total of 286 cycles. Cache 3, we missed 11 out of 12 times. That's a 92% miss rate. And the total cycles, put in the numbers, 12 accesses. This time the access time is 5 cycles. The misses is 11 out of 12. This miss stall time once again is 25. Do the math, we end up with a total of 335 cycles. So there's question 2. Before we do question 5.10, need a little bit of more explanation here. So back to chapter 5. So now we need to know how to measure performance. So we're going to skip over the write cycle times, this kind of formula. We're going to use AMAT, which is called average memory access time. So we can say it's simply the time for a hit in the cache plus the rate of miss times the miss penalty. So no matter what, we have to access the cache. So we got to measure the time for a hit plus the possibility we have a miss and how many cycles that's going to cost me. So using that, then we can actually look at question 5.10. To go to the exercises here. And in 5.10, we're comparing 2 caches belonging to 2 different processors. So we're going to say P1, processor 1's cache, L1 stands for level 1, so the first level cache, has a size of 2 kilobytes. Might seem small, but a lot of times caches are small. As we said, smaller is faster. So P1's cache is 2 kilobytes. I'm not sure if this really matters with the problem, but what we need is the miss rate is 8%, and the hit time is going to be 0.66 nanoseconds. First thing, we say the hit time determines the cycle time for it. Why? Well, if the time for a hit, if we hit within 1 cycle, we want to know the respective clock rate. The clock rate is just the inverse of the cycle time. So if the cycle time is determined by the hit time, the respective clock rate is just going to be the inverse of this number. Not sure if I can highlight it. Guess not in Zybooks. It's going to be the inverse of this number for P1 level 1 cache, and this clock rate for processor 2's level 1 cache is going to be the inverse of this. So we simply just take the inverses. 1 over 0.66 is going to be a 1.515 gigahertz clock for processor 1's cache, and 1 over 0.9 nanoseconds is a 1.1 gigahertz clock for processor 2. Now we need to figure out what is the average mean access time excuse me, for processor 1 and processor 2. So the question now is asking, what's the average memory access time for P1 and P2 in cycles? Usually we do this in nanoseconds, but I'll show you how we can do it in nanoseconds and in cycles. So given the information we have of an 8.0% miss rate and a 0.66 hit time for P1 and a 6% miss rate for P2 and a 0.9 hit time for processor 2's level 1 cache, we say the hit time, as we showed, is dependent upon this. So the hit time is 0.66 nanoseconds. The miss rate for processor 1 was 8%, I believe. Yep, 8%. 8%. And the penalty time is 70 nanoseconds. Where do we get that from? Right here. Penalty time is the time to access main memory. 70 nanoseconds. Notice we don't need this 36% of all instructions access data memory for the question. Not sure why this is put in there. Maybe it's for the rest later parts of the question. But right now we just need the 70 nanoseconds for the main memory access time. Because if we don't find it in the cache, we have to find it in main memory. So that's our penalty time, 70 nanoseconds. So we do the math, we end up with 6.26 nanoseconds. This is how the question will be asked on the midterm, just in terms of nanoseconds. What's the average mean access time? But since the question asks cycles, we can take the same kind of question and translate it into cycles. So the cycles for a hit in the level 1, as we said, the hit time determines a cycle, so it's 1 cycle if we have a hit. Excuse me. The miss rate's going to be 8% once again. How many cycles to access main memory? Well, if it's 70 nanoseconds to access main memory versus 0.66 seconds to access the cache, and we said 0.66 nanoseconds determines the clock cycle, we figure out how many clock cycles 70 nanoseconds equates to. We do the division here, and since you can't have half a cycle, take the ceiling. This would turn into 107 cycles times our 8% plus 1 cycle for the hit. So we'd have roughly, this is an approximation here, because once again you can't have a fraction of a cycle. We're saying on average, because this is average mean access time, 9.56 cycles. Once again, this is kind of a strange way to do it. So on the exam, I would just ask you nanoseconds with the math. P2 is the same thing, different values. So we'll have the hit time for the level 1, in this case is 0.9 nanoseconds. The miss rate, if we go back to the chart, was 6%. And the time to access main memory, once again, is 70 nanoseconds. So we'll end up with 5.1. And since the question said do this in cycles, if we convert 70 nanoseconds to access main memory, and if we had a 0.90 nanosecond clock, this converts into 78 cycles for main memory, 6% of the time we access it, 1 cycle for the hit, we would end up approximately 5.68 cycles. This part of the question, 5.10.4. This time what we're doing, we're using different information. So once again, we have a miss rate and a hit time, but now we're dealing with a level 2 cache. So we have a level 2, which is just one more level after the level 1. It's going to be bigger, it's going to be slower. So between the level 1 cache and main memory, we're going to stick a larger level 2 cache. If we add in this level 2 cache, how does this change our formula? We're just going to extend it. So now the average mean access time will be the hit time for the level 1 plus the miss rate for the level 1 times the access time for the level 2. We extend the formula and say plus the miss rate for the level 1 and the miss rate for the level 2. So if we miss in both the level 1 and the level 2, and then access main memory. So we plug in all our values and we have 0.66, that's our hit time for the level 1. 8% of the time we're going to miss in the level 1. To access level 2 is 5.62 seconds. And 8% we miss in level 1, 95% we miss in level 2, 70 nanoseconds to access main memory. Do all the math, we end up with 6.4296 nanoseconds average mean access time. Now the other part of this question, what was the other part of this question? The other part of this question was, if we did this in cycles, that's right. If we did this in cycles versus time, we could plug in the following. Once again, we just have to round up how many cycles this is going to end up being, how many cycles this is going to be. We could go through the math, but in the interest of time, you can go through this. There's the formula, and we're going to end up with 9.852 cycles. Once again, this is better of an answer. This rounding up just seems like more work, and really we should measure it in nanoseconds. But if we did cycles, if we round up here so that we don't have fractions of cycles, we can get this, but then notice we still get an approximation which still has fractions of cycles. 5.12, we'll continue this because it's once again average mean access time. Actually, the question originally was asking right here the CPI, cycles per instruction, but really it's better to measure this in average mean access time. So we're going to do that. Given all these numbers, we say if the processor speed is 2 gigahertz, it's a 0.5 nanosecond clock. And if the first level cache determines the cycle time, then 0.5 nanosecond clock means a 0.5 nanosecond hit time. Second level, if it takes 12 cycles and we base it off of the hit time for the first level cache, then it's going to take 6 nanoseconds for the second level. If we had an 8-way set associative, we didn't really get into set associative. This just means you can have more blocks per line for a choice. You can look in the book what really 8-way set associative means. It's just another way to design a cache where you got 8 blocks within a set. Direct map means 1 block per set. 8-way means 8 blocks per set. Once again, I'm not going to get into the details here because the book doesn't really get too much into it. And we're just going to have different numbers. So for this one, we're going to have 28 cycles and a 0.5 nanosecond clock. So this would be 14 nanoseconds. And then we can compare, because that's what this question's asking. It's asking if we had just a first level cache, or number 2, a second level direct map cache, or we had a second level 8-way set associative cache. Once again, we don't really have to get into the details. We just have to compare these with the numbers. So if we have only a first level cache, the average mean access time, once again the formula, the hit time for the level 1 plus the miss rate for the level 1 times the access time for main memory. Plug in the numbers, we get 0.5 nanoseconds, 7% of the time. That was the miss rate for the level 1, and the access time for main memory is 100 nanoseconds. Let's reference here. Yep. The first level had a 7% miss rate, and the main memory access time is 100. So if we plug in the numbers, we get this, 7.5 nanoseconds. The second level direct map cache. Once again, we have the hit time for the level 1 plus the miss rate for level 1 times the access time for level 2 plus the miss rate for level 1 times the miss rate for level 2 times the access time for main memory. Plug in the numbers, we're going to get 1.165 nanoseconds. And the third one here, if we do a 2-level 8-way set associative cache, once again, the average mean access time is the hit time for level 1 plus the miss rate for level 1 times the access time for level 2 plus the miss rate for level 1 times the miss rate for level 2 times the access time for main memory. Plug in the numbers, we're going to get 1.585 nanoseconds. Given all this, what's the best approach? This one, because we have the lowest time. So the best approach would be a 2-level direct map cache. That's it for question 5.12. Before we do 5.14, I'm going to talk about the topic that it deals with. So now we're going to get into section 5.5, which deals with dependable memory hierarchy. We're going to look at what can happen if there's an error somewhere in my address. Look it down to this section here, which is called Hamming single error correcting and double error detecting code. The idea behind this is, what if we have an error somewhere in my code? So for example, if I have this as my code, we can check for parity to see if we have an even number of ones or an odd number of ones. In this case, we have 1, 2, 3, 4, 5 ones. If we want to make it even, since we have an odd number of ones, we append to the end of it a single 1 to make the grand total even. That's what's called even parity. That way, if any of these bits flip, we would know there's an error because this count would be off. If I change any of these ones to 0, now I'd have an even number of ones, and this 1 to make the grand total even would actually make it odd, which means there would be an error. So that's what's called parity code checking of 1 bit. But we can extend it to a Hamming code where we not only just put 1 bit, we put several to check and see if my total is even or odd in what I'm checking. So if I have a long enough code, like here, I'm going to have various check bits. Notice each of these is a power of 2. And bit 1, instead of like before, where we check all the bits of my code, like we did here, to see if I have an even or odd number of ones, each bit in my Hamming code here is going to check a certain set of bits. So bit 1, this parity check bit, is going to check all the odd positions. Position 1, 3, 5, 7, 9, 11. Why these? Because it's all the bits where the rightmost, we should say position or value, where the rightmost bit is 1. So bit 1 checks all the odd position bits, we should say, in my code. Bit 2 will check in my code position 2, 3, 6, 7, 10, 11, 14, 15, etc. Why these? This is where the second bit to the right is 1. Bit 4 checks everybody, 4 to 7, 12 to 15, 20 to 23, etc. Where the third bit to the right is 1. And bit 8 checks bit 8 to 15, 24 to 31, 40 to 47, everybody where the fourth bit is 1. So we'll show this by example. If we have 1, 0, 0, 1, 1, 0, 1, 0 as my data, I stretch this out into this Hamming code right here. So notice originally I had 8 bits. I'm going to put in 4 check bits. So as we said, every position, that's a power of 2. Position 1, 2, 4, 8, we're going to set aside for our check bits. So that's why when I write out this code, 1001, 1011, I write it this way. I leave bit 1 for the check bit 2 for the check bit, then I start writing it out. 1001, 1, 001, I skip this because this is position 4 with the check bit. I skip position 8 because that's a check bit, and the rest of it is 1011. This is how I convert my data, my 8-bit data, into a 12-bit Hamming code. Every position that has an underscore here or dash is a position that's a power of 2, and I set that aside for my check bits. Then I go through. Check bit 1 will check 1, 3, 5, 7, 9, 11. Notice there's nothing for 1 here because we're going to set that. So I check 3, 5, 7, 9, and 11. And when we check these positions, we notice bit 3 here is a 1, bit 5 is a 0, bit 1, 2, 3, 4, 5, 6, 7 is a 1, and then the 9th position here is a 1, and the 11th is also a 1. How many 1s do we have? We have 1, 2, 3, 4. Since we have 4, that's going to set my parity bit here to be 0. Since I have an even number of 1s, 1, 2, 3, 4, that's going to set this bit to be 0. Same thing, parity bit 2 will check position 2, 3, 6, 7, 10, 11. Once again, 2 is not set yet, so ignore it. But we check position 3, 6, 7, 10, 11. How many 1s do we have? 1, 2, 3. Everything bolded here is what we're checking. So we got 1, 2, 3. Since it's odd, we set that to 1. So parity bit 2 will be set to 1, as it is here. Position 4 checks 4, 5, 6, 7, 12. 4, 5, 6. Well, 4 isn't set yet. All right. This is 5, 6, 7, 8, 9, 10, 11, 12. We're missing something here. There should be a 0 on the end of this. It's missing. Author's mistake. There should be a 0 right here. But anyway, same count. We only have 1 1 that we're counting. So since it's odd, we set bit position 4 right here to be a 1. And last but not least, bit position 8 checks position 8, 9, 10, 11, 12. Since we don't have 8 yet, that's a dash, that's a blank, but we check 9, 10, 11, 12. We got 2 1s, so we set it to 0. So this is going to be our complete correct code. Now why this is a checking code It's because if we flip bit 10 right here, that's going to be an error. So we flipped it from 0 here to 1 here. How we can check this, we just go through one more time. We do parity bit 1, 2, 4, and 8. We go through, and each time we should have an even count. This time, we do have an even count. There's going to be 4 ones, so this group is okay. So parity bit 1 did not detect an error. Parity bit 2 here will check an error because we find 5 ones, 1, 2, 3, 4, 5. So there's an error somewhere where parity bit 2 checked. Parity bit 4 will check 4, 5, 6, 7, skip 8, 9, 10, 11, and check 12. We're going to only detect 2 ones, which is even, so this is not going to detect an error. Parity bit 8 will check 8, 9, 10, 11, 12. 3 ones, that's odd, so there's an error. Since parity bit 2 and parity bit 8 detected an error, we just add them together. 2 plus 8, we get 10. Therefore, we detected the error in bit 10. We correct it by inverting it, and as the author said, voila, there we go. That's how we can correct errors in addresses, by using parity bits to check. And as an example, the author gives us this one. We go to the exercises in chapter 5. Go to exercise 5.14. And we're not going to deal with the other kind of codes here. We're going to focus on the one that we actually considered here, the single error correcting, double error detecting code. We don't need to know how many bits to protect a 128 bit. Really what we want to look at here in this problem is if we have practical example. Where's our practical example? 8-bit words. Oh, here we go. It's right here. So if we read the value 375, we ask the question, is there an error? And if so, correct the error. So in hexadecimal 375, if we write this out in binary, we're going to have this. This is what it's going to look like in binary. 375. There's 375. And as I said, the parity bits are underlined in bold text. We're going to number the bits C1 to C12, left to right. And so we're going to check if this is what we're originally given. We want to know, is there an error? So this was set up for us. So we figure out the new parity bit 1, parity bit 2, parity bit 4, and parity bit 8 in our code. One way to do it is just XOR all the odd bit positions for P1 starting from 1. P2 we're going to XOR every 2 positions starting from 2. P4 we're going to XOR every 4 positions starting from 4. And P8 we're going to XOR every 8 positions starting from 8. So we just go through and XOR because that's another way to count the ones. So if I go through position 1, 3, 5, 7, 9, 11, I'm going to discover position 1 was 0, position 3 is 1, so 0, XOR 1, XOR 0, XOR 1, XOR 0, XOR 0. Same thing as counting the ones. I got 2 ones, so no error will be detected. P2, I do the same thing, just all the positions it's going to check. 2, 3, 6, 7, 10, 11. And so we XOR, which is just count the ones. I got 1, 2, 3, 4 ones, 0, no error detected by P2. P4, I'm going to count the positions. Once again, I got 1, 2, 3, 4, 4 ones, so no error detected. And P8, this time I got 1, 2, 3 ones finally. There's an error detected, but since only P8 detected the error will be in, ironically, the parity bit itself. It's going to be bit 8. So the parity bit was wrong itself. That can happen. So we just correct it, flip it from 1 to 0. This is a small example. The book gave not real substantial, so I added another problem for more practice here. Something that actually deals with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 6, 7, 8, 9, 20, 22, 23, 24, 8. So 28 bits. Here's the hexadecimal reference. 28 bits as more of an example, more substantial to go through. And in this case, parity bit 1 will detect an error. Parity bit 8 will detect an error. Parity bit 16 will detect an error. So since 16 and 8 and 1 all detected the error, we add 16 plus 8 plus 1 is 25. So in this example, bit 25, which is right here, this one right here, is an error, should be flipped from 1 to 0. As we said, as the author said, this is actually a single error correcting and double error detecting. We can actually detect 2 errors. We can't correct, but we can detect 2 errors. So interesting to ask the question, what if there were 2 bits in error? Can we detect them? We can, but we can't correct it. If we have 2 errors instead of 1 bit, the result would look like it was bit 25 was an error. All we need are 2 positions such that these 2 positions, if you XOR them, they equal 25. For example, if bit 18 and 11 were both in error, if both of these bits were in error, 11, which is right 4, 5, 6, 7, 8, 9, 10, this one right here, this is bit 11, then 12, 13, 14, 15, 16, 17, 18, this is 18 right here. If both of these bits were flipped, it would change the result inside of here such that it would actually look like bit 25 was an error, even though it was 11 and 18. Because 11 and 18, if you XOR these 2 numbers together, bitwise, 0 XOR 1 is 1, 1 XOR 0 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0, and 1 XOR 0 is 1. It's going to look like bit 25. So we can detect these 2 errors, 11 and 18. But we can't correct them because it's going to look like it's on bit 25. How do we know it was these 2 bits, or any 2 bits, and not just 1 bit 25? The author actually goes through and explains this, that we add 1 more bit to our data over here. The author says we add 1 more bit. That's how we know if it's 1 bit error or 2 bit errors. We add an extra bit on the very end of our code that checks the entire word or the entire piece of data to see if we had an even number of ones or an odd number of ones. And depending on this, either we had a 1 bit error that we can correct, or we could have had actually a double error that's turned out to be even. So we use one more bit at the very end just to say, did we have one error or two errors? Notice we can't correct the two errors because there's too many cases this can happen, but we can detect it. That's what this question extra problem was asking. What if in fact we had 2 bits in error? Yes, we can detect it, but we can't correct it. That's how Hamming code works. We go through our code, we check certain totals, either all the odd positions, we compare and XOR together, or every 2 positions, or every 4 positions, or every 8 positions to set our appropriate parity bit, and whichever ones are wrong, we just add them together, and that'll tell me ultimately where my error is. That's how Hamming code works. Now we move on to the last and final section of chapter 5. So the last section of chapter 5 we're going to go over is virtual memory. What is virtual memory? The idea is we use main memory as our cache for our virtual memory. So just like we use a cache for main memory, the main memory is now going to be a cache for virtual memory. The idea is we want to handle more memory than we actually have in the computer. That's why it's called virtual. We're going to deal with processes or programs that are bigger than we have storage in main memory. So we're going to have an address here in main memory, and we're going to pretend that we have more memory than we really have by dealing with a virtual address. So an address that can be beyond what we actually have available in RAM, in the main memory. In order to convert a virtual address, which is bigger than we have physically available, into a physical address, we do what's called address translation to map a virtual address into an actual physical address in main memory. Like with the cache, if we don't have something in main memory, if we didn't have it in the cache, we called it a miss. If we don't have what we're looking for in main memory, we call it a fault. When we're trying to access something, but we don't find it in main memory. So we're looking for something in virtual memory, but it doesn't exist in main memory. That's called a fault. So we can take various virtual addresses and map them to physical addresses. If you notice, there's not a lot of rhyme or reason behind this. This block or page, we call them, in virtual memory, this page 0 doesn't have to map to page 0 in main memory. It can map all the way down here, which I think is 0, 1, 2, 3, 4, 5, 6. So virtual page 0 off the disk can map onto any one of these pages in main memory. It's just on demand, so whatever we're accessing first, probably we wanted this page first. That's why this got mapped to page 0 in main memory. And notice nothing maps to page 1 in main memory yet. And then we have page 2, 3, 4, etc. So if we try to access this page right here, page 1 in main memory, this would be a fault. And if I try to access something here also that did not have a mapping, that would be a fault. So it's a whole question of how we take a virtual address, something that can be this big, and convert it to what's physically available as a physical address. The page offset says where we're going inside of that page, which byte or which word or which block, whatever we're after within the page. This just purely translates down. This just converts exactly. The translation comes from taking a virtual page number, running it through what's called a page table, which tells us how we map into a physical page number. That's the whole key. Take a virtual page and translate it into a physical page. I'll show by example here. Hopefully we have a good example. So we have this virtual page number, and we would go through the page table. This is our page table, and look it up and see where it maps into a physical page number. We take the result, the physical page number, and that becomes now the front of my physical address. So once again, if we have our virtual page number, we just look it up inside our page table. We check if it's valid or invalid. In this case, it's valid. So this will be the physical page number that we can use then to reference our physical memory. So the key thing is how we build this page table, how we translate from a virtual page to a physical page. That's the key thing about this. One thing to mention, the translation look-aside buffer. What is this? You can think of this as a mini page table. So it's like a cache version of a page table, translation look-aside buffer. So it's like a small version of our page table, just a mini page table. Since it's smaller, it's going to be faster. Hopefully we can do a quicker reference. We find out if the reference is valid. We're not going to get in the other bits here. Really just we need the valid bit here. Dirty means if the information's been changed or not. And we're not going to get into the reference bit here. It's beyond the scope of what we need to go through. So we got our virtual page number. We look it up. It's valid. We got our page number here, and we can look it up in physical memory. So the TLB, translation look-aside buffer, is just a small version of the page table. So notice I'm looking up virtual page number, whatever this is here, whatever number this would be. And this is a cache, or a small version of the page table. So there's going to be another copy in the page table. The translation look-aside buffer is just a small version. So it's the most commonly referenced virtual page numbers. So if it's in the translation look-aside buffer, it'll also be in the page table. But it might be in the page table without being in the translation look-aside buffer, because this is, once again, just a cache or a small version of this for faster, easier reference. So we got to look through this first, and if it's in here, we translate it into physical memory. If it's not in here, we go through our page table and then translate it into physical memory. If it's not in here at all, because the valid bit's 0, then it's not in the page table, it's not in the translation look-aside buffer, means it's not in physical memory. So we're going to get a fault, which means I got to go to my disk storage here, find it, copy it into physical memory, and then update my page table and my translation look-aside buffer with the appropriate virtual page number. So it works the same way that a cache works with main memory. It's just now it's physical main memory and virtual memory. So here's the whole process. We take our virtual address. First thing we do, we look and see if it's in the translation look-aside buffer. If it is, great. If not, there's a miss here. And then we see whether we write or not. One thing to note, if it wasn't in the TLB, looks like it's missing from this chart, we would actually look it up in the page table. If it's not in the page table, we have an error. I guess we're just showing the best case scenario here. If we hit in the TLB, and then we go to the cache, and ultimately what we wanted was a hit in the cache, but all these other cases show when we could miss. Once again, what's missing from this picture is if we miss in the TLB over here, we have to actually check the page table and see if it hits or whether we have a fault. So I'm skipping through this kind of quickly to get to the example. Okay, we'll go to the exercise. That's really what we need to know. We'll show it by example through the exercise. So here we have exercise 5.16. And I'm looking up these various addresses. We have the hexadecimal version of it, and we also have the decimal version of it. We start off, here's my page table. I'm sorry, this is my translation look-aside buffer. So we're going to have a tag of B or 11, a tag of 7, 3, and 4. And we're going to say for each of these entries, my tag is going to be most likely my virtual page number. And we're going to say what's the physical page number it translates to. This was just filled in for us initially. And we're going to say the time we last accessed, because when we're going to get rid of something, we're going to use what's called least recently used replacement. So whichever one has the largest number, that's the one that's going to be kicked out of my translation look-aside buffer, and also ultimately my page table. So once again, the translation look-aside buffer is just a small version of my page table. So everything in the translation look-aside buffer should be in the page table. So here if my tag is B and it references physical page number 12, down here B is my index in my page table. That's going to be my virtual page number, B or 11. Has a corresponding physical page of 12. So virtual page B or 11 maps to physical page 12 in my physical memory. Here, virtual page 7 maps onto physical page 4. Just double check. 7 maps onto 4. 3 maps onto 6. 3 maps onto 6. 4 maps onto 9. 4 maps onto 9. So all of these are valid. Notice we have a 1 here. We have a couple other valid ones like 0 maps onto 5. That's valid. The ones that are invalid, they don't have a physical page, so we just say it's stored not in physical memory, only on the disk. So we use all this information that's given to us initially to determine these addresses here in hexadecimal. Where do they map to, and how do they change the translation look-aside buffer and the page table when we reference them. So we'll show it over here. So we start off with our address 123D, and decimal, just as a reference, was 4669. This was, in fact, what tag? Oh, this is virtual page 1. I think we're pulling off the first hexadecimal digit here. That's how we're referencing. So virtual page 1, we look it up in our translation look-aside buffer. Notice there is no tag of 1. So that's going to be a fault in my translation look-aside buffer, or a miss. I go to my page table, and also index 1 is invalid because this was sitting on the disk. It's not sitting in physical memory. So this is going to cause a miss in my translation look-aside buffer since it's not in there. It's going to cause a fault in the page table. And since I don't want a fault again repeatedly, I'm going to have to replace something in my translation look-aside buffer. So this is how my translation look-aside buffer appeared. Before I had a fault or a miss by this reference here, I have to change things. What do I change? Well, I find out who is the oldest. The oldest is right here. So 4, which mapped onto 9, is the oldest because it's been 7 cycles since I referenced it. So if I have to replace something, this is the least recently used. I have to replace this. So that's why 1, my virtual page, which will be my tag. Virtual page is the tag. I replace virtual page 4, as we said right here. I will replace virtual page 4, which mapped onto 9. I replace this entry in my translation look-aside buffer, since that's the oldest, with tag of 1, and 1 over here mapped to who? Nobody, but we just take the next available physical page. So since 12 was my largest number I used so far, that's my last physical page. Since that's my last physical page that was used, the next available one is 13. So now 1 will copy into physical page 13. That'll be its place where it's going to be stored. I kick out virtual page 4, and since I just accessed it, my last access of this was 0 right now. Everybody else gets incremented. So the 413 cycle has passed, so everybody gets incremented to 524. Down here, if I do this address, this is going to be virtual page 0. It's a miss in the translation look-aside buffer since I do not have 0 here. But here, there's going to be a hit in the page table because 0 does map onto 5. So this is a hit in the page table. But since it wasn't in the translation look-aside buffer, I have to replace something. The oldest one was right here because that was 5 cycles since this was accessed. So I kicked this whole entry out. That's the oldest. And replace it with virtual page 0, which mapped onto physical page 5 according to this, my page table. So I put that there since I just referenced it. It's been no cycle since I referenced, so it's right now 0. And everybody else that I didn't replace, I increment by 1. So the 240, 1 cycle has passed, I increment it to 351. And I go through all the other examples. One thing about this problem I didn't really like is the author gave this reference here, C049, and C is 12. But if you notice 12, there is no entry 12 in my page table, which means it is out of range, which means over here these values aren't going to change. Doing that caused it out of range. Looks like I made a mistake here with, I think, some of these values. I think this should be 8 and B, or 83B, 83B, because once again, if this was out of range, it should not have changed anything in my page table. I think I made a mistake here with the 083B. I think that was okay, but this should be 0B or 083B, the same. this example right here, since it's out of range, is not really valid. I will not do that to you on the exam. I will not give you something out of range, as I said. I will not do that to you on midterm 3. I'll give you everything that's valid in range. And so this is the rest of the examples, once again. And you can go through it if you want. Here's the numbers as reference. And most likely this kind of question will pop up on the midterm, but I will not give you something out of range because there's no real way to answer this. There is no way to fit this in the page table. But this just shows how we can convert virtual pages into physical pages and how we can actually make a copy of something that's on the disk in virtual memory into physical memory. How we know where it's at, we use the translation look-aside buffer as a reference. And if there is a miss in here, we adjust everything so that next time we can find it in the translation look-aside buffer, the physical page, so that we can do our reference. Once again, I'm going to post this up on Canvas right after this talk. I had to do this in various pieces because there's various distractions, but hopefully this will look like one clear, clean looking video. You might see a couple jumps. That's just where I was piecing pieces together, but I will upload this as soon as possible, as well as the solution set. And if any questions on chapter 5, please email me. I'll try to check my email as quick as possible and answer as quick as possible. And otherwise, have a good week. Stay safe, stay healthy, stay at home as much as possible, and take care.